Okay, so I thought we'd take a look at a couple more examples from linearization. Okay, so here's one that's typical in the homework. It says using either a linearization function or the differential, approximate this guy, the square root of 121.2. Hint, you'll need to define f of x, x, and dx, and you have to do that with all your problems. So, okay, so what's happening is I know what the square root of 121 is. It's 11. Yay! But here's 121. What we're going to do is go a little bit farther, as we always do. In fact, we're going to go to 121.2. So your delta x is actually 0.2, isn't it? So that's one thing that's defined, but there's other things. All right, so let's define them. So the function we're actually looking at or playing around with is the square root function. Where we're starting, x, if you will, is 121. But then we're going to bump it up a little bit, call it dx. It's going to be 0.2. So that's what I mean by, let's identify this stuff. If we are using the linearization function, which is a good idea, if we're approximating, it's a good way to go, then we remember that it is f of a plus f prime of a times x minus a. I should have said maybe instead of, if I'm going to use that formula, then I'm just going to, I'm going to call this a. A is 121. All right, well, it looks like we need a derivative. So in red, right next to it, I'll say f prime of x. Remember how to derive square root? I have it memorized, 1 over 2 radical x. I like knowing that one. It comes up quite a bit. So that's our function. So here we go. Our linearization function is f of a, which is the square root of 121, plus f prime of a, which is 1 over 2 square root of 121, and then x minus a, which is 121, like so. So our function says this. It's 11 plus 1 over 2 times 11 is 22, and then we have x minus 121. Okay, use that to compute what if x is equal to 121.2. All right, so I'll say L of, I'll put that in red, 121.2 is equal to 11 plus 1 over 22, and then 121.2. You see how this guy, this guy is really your delta x minus 121. So the computation is 11 plus, I'd write it as maybe 0.2 divided by 22. And what I got as an answer for that one was 11.00909. And so that is our linearization approximation for the square root of 121.2. Now I didn't do this, but just for fun, I'm going to get the calculator right now and just go, what is the square root of 121.2? And it says it's 11.009087 whatever. So it's really close. Okay. If you decide to use the differential dy is, excuse me, it's equal to f prime of x dx. For this problem, it's 1 over 2 radical x times dx. For these numbers, it's 1 over 2 radical 121 times 0.2. So it's really that 0.2 over 22. It's this portion of the linearization right there. So it's interesting to note that you can see the differential inside the linearization every time. Okay, so all you really have to do when you're done with that is add to it the square root of 121, and you get the same answer. So you can use the differential also. The differential again tells you how much it changes, but then you have to tack it on to where you started, which is the square root of 121 is 11. So 11 plus that will do the deal. Okay, one more example. I know you can pause it. All right, and this is number 34 on page 257. It says the radius of a circular disc is given to be 24 centimeters with a maximum error of 0.2 centimeter. Use differentials to estimate the max error in the calculated area of the disc. What is the relative error? What is the percentage error? Those are two things we haven't done yet, but they're pretty easy. Okay, so, all right, what we have to do is I'm going to use a differential. So you might start with, gee, I don't know, dy is equal to f prime of x dx. Looking at this problem, what the heck is f of x? And, you know, all that stuff. What's a? What the heck is happening here? Well, remember, they gave it to us, but we have to do a little bit of work. It's a circular disc with a radius that's 24 centimeters. And they're interested in the area. Well, that's easy. I know the area of a circle is pi r squared. That's a nice function. If you want x in there, you can. You can say f of x is pi x squared. That's the area function. Okay, cool. And guess what? A is 24. Right there. Okay? So, what we'll do is we'll fit it in. We'll just go dy is equal to f prime of x dx. Okay, so let's do some work in red. We know that f of x is pi x squared, so f prime of x is 2 pi x. Okay, got it. We also know that, here's the thing, this finally comes into play, the point 2. So if we're on a number line, we're at 24, and someone says, I measured it pretty good. It could be a little bit off, though. By how much, you ask? Could be off by as much as 0.2. Well, that 0.2 is your dx. Okay, that's the change in x along this for this function. So for us, what we're getting is 1 over, whoops, wrong function, Weber. It is 2 pi x times dx. Let's put the numbers in and figure this thing out. So it's 2 pi, the x is the a, okay? We're starting at x is 24, and then you bump up. So you're going to get 24, and then times 0.2. I did this calculation. I got roughly 30.159 and change. And you know what this is? It is a jump in the area, so it is square centimeters. Okay, that's the error. In this language, you have it 24, but then it might be a little bit off here, just a little bit off. So we'll say it's 24, but there might be an error of 30. That's a lot. That's a lot. Unless you talk about relative error. Relative error is, I would say, it's the error you get, which we just got, divided by the area that we would normally think it was. So I was thinking, you know, that could be a formula like something like that, okay? The actual function value and then the error divided by it. So how big is the error compared to the actual area? Well, what we end up doing is we take that 30.159 and divide it by pi times 24 squared. And when I did that, I got an answer of 0.0166, and it went forever. And that's a relative error right there. The last thing is percent error. What is the percent or percentage error? Well, you take your relative error, and all you do is turn it into percent. So what we get is, well, let's see, how do we do that in old school stuff? 1, 2. Sure. What we get is about a 1.6 bar, maybe, percent, or 1.7%. So actually, 30 is a big number, but compared to the actual area turned out to be 1,809 plus whatever. And so compared to the actual area, it's actually pretty small. I still think 1.6 percent error is kind of big. But that's it for this one. There's a couple more examples. I tried to make this one short and sweet. Okay, last one for this chapter coming up.